So today we're taking a look a little bit deeper into kinetic molecular theory, and we're looking at effusion and diffusion. What they are, what the differences are between them, how they kind of are relating in here, as well as we get to some other aspects later on. Well, first of all, a good reminder to think about here is that kinetic molecular theory tells us that average kinetic energy is proportional to your temperature. So, and your temperature is also be proportional to your average kinetic energy. That's what measures it. Temperature is that measure of kinetic energy. So as your temperature goes up, you're going to have a higher kinetic energy. And kinetic energy, we know, means particles will be moving faster. And vice versa. Lower temperature, lower average kinetic energy. Well, what happens if we take two substances, two gases, for example, like helium and xenon? And let's say we're going to have them both at the same temperature. If they're at the same temperature, the only thing that temperature measures is average kinetic energy. So therefore, they're going to have the same kinetic energy. Well, what's going to happen in this case in terms of thinking about what's happening with the particles and the particle movement in this case? Well, beginning here, we take a look at the masses of our elements. Helium is an atom with a mass of 4. Xenon has a mass of 131. Well, if we think about kinetic energy for a second, we know that kinetic energy is equal to 1/2 mv squared, where m is the mass of your atom, and v would be the velocity. So you can see if these things have different masses, then there's no way that they can have the same speeds. With a much smaller, much smaller mass of 4 for the helium atoms, it's going to have a much higher velocity than the xenon particles do. So smaller particles at the same temperature to have the same kinetic energy have to move faster, and at the same temperature, heavy particles will always move slower. We don't want that happening there. Drawing lines on my screen. And this is something we call the root mean square speed, which we represent by the letter U. Don't know why it's U, no idea, but it is. And what the root mean square speed is for any atom or compound or molecule is U is equal to the square root of 3RT over capital M. Now, in these cases, these letters all mean something. R is something called the universal gas constant. And the universal gas constant has a number of different values depending on the units that we're using for it. In the case that we're going to be using it for the root mean square calculations, we're going to be using 8.314 joules per mole Kelvin, which is the same as 8.314 kilogram meter squared per second squared mole Kelvin, because that's what a joule is. It's a kilogram meter squared per second squared. Okay. T is our temperature in absolute terms, and that means it's going to be in kelvins, and M is the molar mass of our compound or our element, which I don't have listed there, but that's what it is. Molar mass, T is temperature in kelvins. So we can find out what that root mean square is of any substance pretty easily if we know the temperature and its velocity. And that's what we're kind of look at first in this slide, is we're going to look at finding the root mean square speed of nitrogen gas at room temperature, which is 25 degrees Celsius. So our equation again is 3RT over M, and our temperature we have to change from degrees Celsius 25 into kelvins, and to go from Celsius to kelvins we just add 273. So 25 plus 273 is 298 kelvins. R we already know is 8.314 kilogram meter squared per second squared mole kelvins. The molar mass of nitrogen N2 is 14 times 2 is 28. So when I plug those three numbers into my equation, I get a root mean square speed of 515 meters per second, which, to put in perspective, is 1,150 miles per hour. So at room temperature, those molecules of nitrogen in the air around us would be normally hitting us at 1,150 miles per hour. Boy, does that hurt every once in a while when you feel that? Bam, those molecules banging in you all the time like that at that speed. Whew. Not really, right? Yeah, no. Well, okay, now we know that what's happening is these particles are all moving. What we can take a look at are things called effusion and diffusion for today. And basically, when we look at effusion first, we talked about diffusion a little bit in class, and we did the butyric acid and made the room nice and smelly for us because we're showing how it's spreading out. We briefly talked about effusion, but I want to talk about a little bit more today yet. And basically, what this is, it's the rate that a gas can escape through tiny pores or pinholes in a device or in a substance. So it's kind of an important topic in this case, mainly because effusion rate ends up being inversely proportional to the square root of your molar mass. So the lighter a gas is, the faster it will effuse. It will escape through tiny pores. And a really good indication, a really good example of this happening is with a balloon. Balloons are made of latex, and latex has lots of little pores in it. If you've ever had a helium balloon that you've had for a while, you try to keep it around for a little while, you probably notice that after a few days, if you don't put that little liquid in it that coats the inside of it, that the balloon deflates over time. And a helium balloon will deflate faster than a regular air balloon. And that's because helium has a much smaller mass than the normal things in air, nitrogen and oxygen. Again, helium has a mass of 4. Nitrogen and oxygen have masses of 32 and 28, so they're much heavier. So those particles at the same temperature will be moving much slower, so they're not going to be able to escape as fast. Plus, we're going to see something else has to happen in order for effusion to occur. So again, lighter gases will effuse faster than heavier gases, and vice versa. Heavy gases will effuse slower than light gases. Now, we can actually write some expressions for this, and we have a law called Graham's law of effusion, and it applies to diffusion as well. So a lot of times we call it Graham's law of effusion and diffusion. And basically it's saying that the rates of effusion or diffusion are inversely proportional to the ratio of their molar masses. And so what we're going to do is write, in this case, R1 over R2. Yeah, that's an R on the bottom. I know, let's make it more of an R there. So that's a rate of gas 1 over the rate of gas 2 is equal to the square root of the molar mass of gas 2 over the molar mass of gas 1. So if we know the molar masses of our two compounds, we know the rates of effusion of one of them, we can find the rate of effusion of the other one. Now basically, when we take a look here, I have a diagram here at the bottom. What's happening for effusion is on the left-hand side of either of these containers, we have our gases. The right-hand side was a vacuum, was an evacuated chamber. And there's just one little tiny pinhole in here. Now, in order for effusion to happen, you have to have a molecule or a particle collide directly with that pinhole. You can't go through unless it hits the pinhole. Well, you can see that if a gas is lighter, then at the same temperature, it has to be moving faster. The faster it's moving, the more distance it's going to cover, the greater the chances are that it's going to hit that pinhole to be able to go through. And here we have an example of helium, which is, again, very light. And then ethylene oxide, C2H4O, which is going to be a lot heavier. 24 plus 16 is 30, 44 is what we have versus 4. So it's 11 times heavier. So it's going to diffuse way slower, effuse way slower. And that's that idea of a particle in the balloon is going to be bouncing around until it hits directly on that pore for it to escape out. And again, lighter gases do that much faster. That's effusion. Diffusion, on the other hand, is going to be similar, but instead of having a gas escape through a pinhole, it's going to be the spreading of a gas through space or through another gas, like with the butyric acid. It kind of spreads throughout the entire container, spread throughout the entire room, then spread down the hallway as it's going between. And we said diffusion happens pretty easily with gases because our particles are pretty spread out, and so it's easier for them to go through. But you got to remember, and the same thing is true again here too, that your diffusion rates are faster for light gases, and again it's the exact same law. R1 over R2 is the square root of M2 over M1. Now I have circled over here, something called the mean free path. And basically what that is, the mean free path is the distance that a gas particle can move before it hits something else. Now if you're at sea level, then you have a pretty high density of gases. And so the speed of diffusion is going to be slower than what those molecular speeds are. It's not going to be 1,150 miles per hour. or 515 meters per second, because it's only going to move so fast before it hits something else. It's going to change direction. So remember, elastic collisions are going on here. Every collision is elastic. They're just going to keep bouncing off of each other. So every time they collide with another gas particle, they change direction. And that mean free path is how far they go before they hit something. Now, with gases at sea level again, you're talking about somewhere on the order of like 60 nanometers at sea level. That's not very far before they have a collision and before they move. So that's why we're going to see a slower diffusion rate for gases and what those molecular speeds are. They might be moving at 515 meters per second, but they're only moving 60 nanometers before they hit another gas. At 100 kilometers of altitude, now you've got a path of about 0.6 meters. That's a really good 0.6. That's even worse. Let me fix that here for us. Which is like 1,000,000 times farther. Or 1,000,000,000 times farther, actually, in this case. So 10 to the 9th, 1,000,000,000 times farther. So it's going to travel 1,000,000,000 times farther before it hits something. So your diffusion will happen even faster at higher elevations. Okay, so that's a little bit about effusion and diffusion, and we'll be working on a couple little things like that deal with this in class and some gas properties. And then when I get back, we'll talk about pressure and barometers and manometers and Dalton's law of partial pressures. Look forward to that.